we're going to begin by looking at some numbers. But rather than just throwing huge numbers out and a bunch of facts in the air and trying to catch them with a trawler's net, because it's not very fun doing that, I'm going to give you some perspective so we can hopefully and truly see the fullness of what is being suggested. Psychologically, 13.8 billion, bookmark that number, we will come back to it, doesn't seem a big number in today's world. In 2023, there were 3,323 billionaires worldwide. The most billionairest of them all, and was and still is, Elon Musk, with an estimated 328.5 billion US dollars as of March 2025. That's a lot of billions, and makes our number of 13.8 billion years seem paltry in comparison. This figure, the approximate age of the universe, has been estimated remarkably accurately by two independent, and some might say even a friendly level of competition between them, spacecraft. The Wilkinson Microwave Anisotropy Probe, WMAP, I've been dreading saying that for the past week while I've been planning this, and Planck Probe. When the universe began 13.8 billion years ago, the bit that we can see needs explaining, because this is getting very, very technical now. So I want to explain this by doing a little experiment with you. So if you'll just bear with me 1 second, I'm going to fetch some balloons and a marker pen. What am I going to do with some balloons and a marker pen? You crazy man. Right, what we're going to do first, other than dropping the balloon, is blow into it. Some of you may have seen this done before. I'm going to demonstrate the expanding universe here. So we're going to draw with our marker pen. No, we're not, because it's not working. That's failed miserably, hasn't it? I'll just explain it instead. So when the universe expands, test things, Richard, before you speak publicly. I think that's what we can take away from today. So when the universe expands, we have, let's say, this wonderful table of 4 people here. Everything is moving away from each other because the universe is expanding in every direction. So if we imagine that our place in the universe is one of those tiny dots, or one of the people at the table, from our perspective, every other thing we can see is moving away from us at the same point as the distances increase. We'll get to a point where those other dots disappear over the horizon. While we are all familiar with how horizons work on Earth, maybe not those who believe in the flat Earth, maybe there's a bit of disagreement there. Don't know if we've got any flat earthers in the room, have we? No, good. That makes it a lot easier for the question and answer section in a bit. The cosmological horizon, as it's known, is not there because of curvature, but because the universe is expanding at a faster rate than light travels. So the light from beyond the horizon quite literally never reaches our eyes. So how do we work out this horizon? The distance between two objects is known by cosmologists as the proper distance. This is the distance between any two given people at the table we looked at in our experiment. And this is always getting bigger. The cosmological horizon in the observable part of the universe we discussed earlier is 46 billion light years away if we consider this proper distance. Hence, 92 billion light years away if we consider the whole observable universe. And that might seem confusing at first, but if you imagine you stood 4.6 miles away from the horizon, then you turn round and you're 4.6 miles away from that horizon, altogether, the observable part of it is 9.2 miles. It's the same principle. Anything that within that horizon we can see. Anything over the horizon we can't. Simple? Not quite. We can't see back all the way to the beginning of the Big Bang. In fact, we cannot see anything before about 380,000 years after the Big Bang, when the temperature of the universe dropped to a positively chilly 3,700 degrees Celsius, which was known as the era of recombination. This allowed protons and electrons to combine and form the first atoms before the universe was full of plasma, and that was known as the radiation era. This wouldn't allow these atoms to form. Only when the universe was cooled enough for the formation of atoms were photons free enough to travel, and the universe became transparent enough for us to see the most distant past. So to simplify, protons, electrons and photons were at a party. The organiser had the heat turned way up, and because it was so hot, nobody wanted to touch the sweaty person next to them. Everyone was filling the spaces in the room evenly, so the photons couldn't move freely around the room. Someone eventually turned the heat down enough so that the electrons and protons got close enough to each other to think, I fancy a bit of that, and coupled up, leaving the photons enough room to jig away on their own. And that is how the universe started a great big party in the sky. Good, got that? Let's move on. The free distribution of photons caused what is known as the cosmic microwave background radiation, or CMB. How the discovery of the cosmic microwave background radiation came about is probably one of the most famous in science, and includes pigeon poo from a pair of exceedingly troublesome birds. That was confused by the interference from the Big Bang. The people who discovered this were Arno Allen Penzias and Robert Woodrow Wilson. They're the team behind the famous pigeon poo story, and they won the 1978 Nobel Prize for Physics. Not for cleaning up pigeon shit, but for discovering the microwave background radiation. With that discovery, we have definitive evidence for the Big Bang theory.